Okay, hello everyone. So imagine or not, we have a last day of the class today, except for a final exam. So we managed the semester in spite of pandemic, in spite of online class. Somehow we managed this, which is great. And basically you realize we passed actually the entire syllabus. Okay, what we did not do this year, what I typically used to teach, as the last two lectures, I used to teach Otto and diesel cycles, introduction of basic idea about air standard cycles, about applications to engines, but it's supplementary and you will learn it in class 321 if you take it. So it's really okay that we finish at this point. I did not start it because I really want you to dive deep in isentropic efficiencies. So we did it. So again, let's finish everything today. And today I want to give you a little bit more hints about your homework and about your exam. And we finish at this point. Yeah, please again, last time I say please evaluate this course if you did not make it yet, because we need to close survey. Not everyone did it yet. Also, please submit your homework. Yes, it's not by noon, it's by night, today night. We give you this extension. Unfortunately, we don't give you more extension because it's mandatory that we finish semester now. So I cannot give you assignments beyond today. But I still want to give you some hints which may help you in your homework. So I'm sharing my screen and what I want to tell you. So basically, one of the key points we consider this week, it was what? It was isentropic efficiency, right? Isentropic efficiency. So this is something important, and please realize how to deal with it. We discussed, but when I see what happened at help session, I still see that some students used to confuse. So please understand very basic idea. Okay, you have your real actual device which exists. Okay, let it be turbine, let it be compressor, let it be something else. And you have your idealized device. It's not your device, it's another device which does not exist. But you consider it because you want to know how much space your device have to improve. This is ideal device, this is your device. Ideal device is how your device would be if it was excellent, if it was isentropic. And you compare them, right? They don't coexist. Sometimes people ask, okay, what formula should I use? Should I use H2A or H2S? The answer is like this. Don't think about formula, think about physics. Don't employ formula if you don't understand where it comes from. You may really do a mistake. Understand this. So what happens? You have state one in the inlet, but you actually have two states too. Actual state two, right? Actual state two, and hypothetical state two. How it would be if your device was isentropic. So they're different. Pressure in these states are the same, but they're different. Yeah, some people say pressure is the same, but temperature is different. That is convention. Because with the idea about your turbine or compressor, it's measured by pressure, right? So basically, you want your ideal device to reproduce real. So that it is. You have state one and you have two state two, actual and hypothetical. And solve the problem like before. Identify H1, H2A, H2S, find isentropic efficiency. Or vice versa, you may have isentropic efficiency, how it many problem in your homework, and you will be able to find state 2 or state 1. Some people say, okay, so where should I apply mass flow rate? To actual process or to ideal? Well, that to both of them, they're different. You can describe device 1 and device 2, right? The only good idea about ideal device that you have equation that S2 is equal to S1, while this is not the case for actual device. In the actual device, entropy is generated. It's generated from scratch. Does it make sense for you or not? Do you understand this, please? Okay, great. So that is, and basically that's what we have. And we can see the examples, and you have these examples in your homework. In your homework is problem 3, 5, 4, and 5. They deal with isentropic efficiency. Key point for you here, please don't confuse compressor and turbine. Formulas are different. And if you realize this diagram, if you understand how it works, everything will go clear. compressor deposits some work. So it will in reality deposit more than you want to deposit. For turbine, it's vice versa. You spend less than you want to spend. Please realize. I remember at the end of last lecture, I discussed this trading way, how we consider it. Please realize. Now, what happened here? Now, also potentially you can talk about what? You can talk about isentropic efficiency for other devices, like a nozzle. For instance, this is a very good illustrative example. So what will be isentropic efficiency of a nozzle? So again, what is the idea about nozzle? What is the idea about nozzle? Nozzle converts enthalpy into kinetic energy, vice versa. So that it is again. So you consider actual nozzle and hypothetical nozzle. Assume you have nozzle like this. So assume this is just example from your textbook, but it's very illustrative. Assume you have nozzle and air comes in. Air behaves like ideal gas. Air comes in and basically it comes like actual nozzle. It comes with let's say with hot temperature 950 degrees Kelvin. It comes in. And now what may happen? So in your actual device, what will happen? In your actual device, you will go from state 1 to state 2 here. So in fact, you will have the following kinetic energy. So in your actual device, what happens? Your temperature drops to, let's say, 764 Kelvin, and velocity generated by the flow will be 640 meters per second, 639, right? In ideal device, how it would be with voice isentropic, what would happen? Your temperature would drop more, your temperature would drop to 748 Kelvin, and your speed will be high. What you may see here, that your isentropic device would work really better than your actual device. And that's clearly understood from here. So basically, because if it was your choice, you would convert entire enthalpy into kinetic energy. If it was your choice, what will happen? If it was your choice, your H2 will be 0 and everything will go to kinetic energy. But we cannot do like this. We cannot because of second law. So what you have here, that the best way you can proceed is like this, correct? So basically what you will have, that here definitely this value will be less than this one. You will spend in reality less, right? And basically what I'm doing here, basically temperature will drop less, and that's why S will be less than H2A, right? And this value will be larger than this. Please realize it. Okay, this is just example how to employ it. So, but key point to understand what you compare to what. You compare your device to ideal device. And here is how it may look like. Here will be your formula. It's the same like a turbine formula. That's for nozzles. You need to know this. You need to know turbines and compressor for your final exam. Something from this still will be in your final exam. Please realize. Now, few more points, few more hints I want to give you. Regarding your homework. So and you still have chance to redo it and submit it tonight. Even potentially you should be able to solve all the problems. We covered everything by Wednesday. So in fact, I told you since chapter 3, key point was what? Key point was to identify the states. And basically you go to table and you need to do interpolation to identify the state. But there are other ways. There is graphical way to identify the state. And that's what I want to show you. For instance, if you look at your text of the problem, what you see here, it's what we call sample calculation questions. So what is stated here? Please find specific and please find specific entropy of water at given condition. And also it's stated here that for problem 2D, you have given pressure and enthalpy and state. Mark the standing diagram. So it means that you can potentially use diagrams, you can use graphic regime to consider it. And the same in your homework, for instance, in your homework, which one? Homework 3 or 4 it was stated, identify state 1. You can do it based on diagrams. What I mean? So if you look at your diagram, if you look at your property tables, you may see there is table 9, which is TS diagram. It's classical TS diagram. Let me rotate it here. So here it is. And let me increase the size. Okay, let me increase the size a little bit. So what you see here? Basically, this is graphical way how you can find the value. So what we have here? So you realize this is classical bell that we considered, right? This is a classical TS diagram. So here we have compressed liquid, here we have superheated vapor and saturated mixture between them. And all these lines that you see, they correspond to some values. They correspond to values of pressure. So let's see the values of pressure. So here all these lines from the left shows pressure is 300 bar. And then you see it's not 300, 30,000 bar. 30,000 bar, it's very big value. It's extremely high pressure. It's quite very supercritical. And here you see the lines for 20,000, 15,000, so on, it goes down. It's 400 bar, 350, 250, and so on. So this is a pressure line. And what happened pressure line? Remember how pressure line behaves. Pressure line goes to your saturated curve, and then it's go at the horizontal line. Remember, constant pressure lines are horizontal line in TS diagram. So that allows you to calculate. And the same for enthalpy. Let's see here is like I see enthalpy is 5,000 kilojoule per kilogram. And then you see 409, 4,900, 4,800, 4,500, 4,000, 3,900, and so on, so on. So these are the lines, and you can consider. So that's another way how you can use graphical. It can be example in this example in your homework. Potentially, we can have it even in your exam, in your engineering other exams like PFE exams. So let me show how we do it. So you find the key point if what you can do. If you know, for instance, pressure and enthalpy, what you will do? You will find your enthalpy line, you will find your pressure line, and you see when they converge, when they intersect. True? Okay, please here. So what I see here, use a simple calculations question. Here, problem 2D, for instance. You stated that your pressure is 4 bar and your enthalpy is 1,600 kilojoule per kilogram. Let's find the state in entropy and set condition. So what shall we do? So you take your tables, and I basically write it here. Yes. So basically that it is. So what we have here? Let me increase questions. That's a good point. For saturated mixture, we could not use pressure, we should use quality because pressure is the same for all the entire mixture. Pressure and temperature will be coupled. Yes, that's a good point. But key point, what we see here, that pressure, it's a nice line that goes here. So let's see what I will show you now. So it looks like you cannot, so what we have here, you know pressure is 4 bar and your enthalpy is given, your enthalpy is 1,600. So what is your pressure? Pressure is 4 bar. So you will take, I will show what to do. You will take the pressure, take a pressure line. So where is 4 bar line? You go or how pressure change. And you see it's very regime. Here are thousands, here is small. So here is 4 bar. So this is a 4 bar value, okay? Let me do like this. This is 4 bar value. So you go along this line. So if you had superheated vapor, you would be here, right? So, but what happened with this constant pressure line when it comes to this point? At constant temperature, remember, you have saturation and you have saturated mixture. So this will be your line. It potentially, sorry, a little bit not straight, but it will go something like this. It is a straight line. It is a straight line. And then it will go like usually in pressure line, something like this. But before we come to this point, your straight intersect enthalpy. So if I go here, what is my enthalpy here? It's 2,600, 2,400, 2,200, 2,000, 1,800. And here it intersects with what value I need. So this is my enthalpy line. And this is my pressure line. They intersected here. Okay, so here is my point. I go here and I find entropy. Does it make sense for you? I found it. And that it is. And you will find that here you can estimate quality and estimate entropy. It will be about 4.2 kilojoule per kilogram. You can do it by interpolation, but you can do it graphically. Similar story, for instance, it was idea in your problem number, which one? When you have turbine. This is a problem number, let me see. I think problem number 5, right, for the turbine. Yes. Yes, exactly. In problem number 5, again, you can two methods how to find it. You can do interpolation classically, or you can do like here. You can do like here. You can, you know pressure, you know temperature. You can identify the state. If pressure is 100 bar, temperature is 600 degrees Celsius, and basically you need to find enthalpy. Of course, you can go to a table, but the good idea is that you can actually get it from the plot, and you will get 7.5 kilojoule per kilogram. For instance, if I go here, you will see it how it is. Here it is, right? So basically, you will take pressure. I'm sorry. Yeah, you will take pressure here. Your pressure is 1,000. So I take it. It's 100. It's 100 bar, right? Correct? What my pressure is here? Let me check. Yeah, your pressure is 100. It's 100 bar and temperature is 600 degrees Celsius. You have 100 bar here. You go like this and see where its intersection happens. But the key point that you know what? You don't know the value when it stops, but you will see where this constant pressure line. Here you have superheated vapor. So you will not go like this, right? It will be not here. In contrast, you will go somewhere along this line. And when you will intersect? You will intersect with line when you have 600 degrees Celsius. So this is your line with 600 degrees Celsius, the temperature line. And this is a pressure line, okay? This is a pressure line, correct? And the point where they intersect, it's what? It's your point. It's your point from where you can get whatever you want. And from here, you will find your entropy. You will find your two S states. You will find this entropy because it's equal to S1 and it is, and then from here you will get S2A, correct? How it is. That is for a turbine. So again, and yeah, I do suggest if you have time, especially when you prepare to a final exam, do this because it's really good preparation, it's a good explanation. Okay? Does it make sense? So just practice. I know it's not easy, but just practice with this graphics, and very often it's simpler than to do interpolation. If interpolation is easier for you, okay, great, do interpolation. If this is easier, do like this. Whatever you want, whatever is easier for you. Okay, now, few more here. So more hints about homework. Do you have any more questions about your homework? So I want to show you something. Because one very good problem in your homework is problem number 6. And it's good because for two reasons. So what's stated here? Let's read the text of this problem. We have air contained in a rigid insulated cubic tank of given age of 1 meter age. So if you have a cube, and it's fed with pedal wheel, and it undergoes stirring process. So at the very between two states. So at the very beginning of your state, you have, and it's air inside. Air, it's your ideal gas. So at the very beginning, what you have? At the very beginning, you have your temperature. Your temperature is 40 degrees Celsius and pressure is 4 bar. And you know it's state 2, temperature is 353 Celsius. So several questions. Find the final pressure. So it means that otherwise identifies the second state. Question B, please determine the work done in the process. And by the way, up to this point, up to point A and B, this is real problem from which section? Which section? Which chapter? Chapter 4, right? So it can be in your second exam. It's problem from your second exam. But then you have question C, please determine the entropy generation, what entropy is generated in this process. And you may realize that some entropy will generate it because of dissipation, it's starting process, correct? That is. So that's why I give this example to you, because you may realize in your final exam, most of your problem will be like this. You will have one question or two questions from initial chapters, but then it will be something about entropy, and you should know all of it. So how we are going to solve it? Okay. You have state 1, which is 40 degrees Celsius, and you have 1 bar pressure. So you know purity, you know state 1, you fully identify. How to identify state 2? How to do it? How to identify state 2? You know temperature. Do you know pressure? How to find it? The key point to remember, yeah, please. The key point to remember is ideal gas law. Excellent. So ideal gas law. So you employ ideal gas law, but when you employ ideal gas law, you should realize the following, and you will see here. You can do the following. Write down equation ideal gas law for first state, for initial state, and final state. And what is nice here, that you have a rigid tank, right? Your volume does not change. So when you divide it, you will have the pressure ratio. It will be T2 over T1. Pressure is proportional to temperature, like for ideal gas. Why it's nice? Because you actually don't need to what? You don't need to identify M is equal to and find M. You just have it like this. And so what you'll have, what you put instead of T2 and T1. So what is T2? What you will do here? You will say it's equal to what? You will write 353 over 40, right? Yes? Exactly. Exactly, that's the most important point. You need to use Kelvin scale here. It's Kelvin, temperature is in Kelvin. And you should switch to Kelvin. And you may realize that when you switch to Kelvin, now something nice will happen. That T1 will be 313 Kelvin and T2 will be 626. I intentionally give you these numbers. And if you take the ratio will be nothing but what? But 2. Nice? It's much faster than calculator of M and so on in volumes. So you will know state 2. Now, second question. Find work done in this process. So what is work done in this process? What do you think? It will be, no, it will be not 2 bar, it will be 4 bar, it will be 8 bar, right? Because pressure grows. Good question. Why can't you use relative pressure relations P2 over P1 is equal to P2 relative pressures? You may see on the chart this message. Very good question, but answer is also quite clear. Because this is not isentropic process. The equations P2 over P1 is equal to relative pressure ratio. It's for isentropic processes. Here it's not isentropic process. Okay? It's not isentropic process. That's all. That's why I tell you, don't employ formulas if you don't know where they originate from. You should always know what to use. Okay, come back to the work, okay? So what is work here? And many students do mistake, especially in the exam, and say that work is 0. And they have justification for this. Why they say? They say because it's rigid tank. PDV is constant. If PDV is 0, dV is volume is constant. Please remember, I don't ask you here about boundary work. Boundary work is 0. Boundary work in this tank, in this particular geometry, is 0. There is no boundary work. But work is not just boundary. Work, remember in thermodynamics, remember chapter 2, we're approaching final exam. Work is everything which is not heat. It's any energy transfer which is not heat. Here you have stirring process. You do work on the system but stirring. You do work on your device. You deposit energy in your device, correct? You deposit work here. You deposit energy in your device. So work will be finite. It will be not boundary work. Or it might be electric heater which added. It will be electrical work. Or it can be magnetic work. So work is not 0. And how you will find it? And the key point to remember that you are back in chapter 4. Write down first law of thermodynamics for a closed system. Nothing like this, correct? Delta U is Q minus W. And what is Q here? Right? What is Q here? People say that you please mute everyone. There is some extra noise, so please mute everyone. Q is 0 here indeed, because why Q is 0? Because it's stated rigid insulated cubic tank. Get equations from here. Insulated means that Q is 0. But boundary work is 0, not your work. So from here you will find what is your work. You will find that your work is U1 minus delta U. It will be U1 minus U2. Mass is constant. And how to find U1, U2? You can get it from your table, or you can approximate it through temperatures. And you will get it. And key point, moreover, I can tell you that you don't need to calculate mass and C as well. Write down your equations. Here you will have, instead of mass, you can find equations from here, PV over RT. Instead of C, you can find it, how it depends on R, and you will calculate. I do want to solve it yourself, but when you have my solution, please take a look at it. It will be really nice, sophisticated formula. But key point to realize is there is work. And you may realize that this work will be negative, right? Why work will be negative? Because T2 here is larger than T1. Work will be negative. And this is okay, right? This is okay because this work done on the system. You're steering pedal wheel, which steers your liquid phase. So it steers it. And it should be like this. No question with this. You steers your liquid phase. You steers it. It should be like this. Because system cannot do work on your pedal. So you will get it. So up to now, it's chapter 5, chapter 4 and 5, exam 2. And then there is a question about what? About entropy generation. So what are you doing here? You are writing balance equation for entropy generation. Here it is, right? For closed system, you have a closed system. Again, what will be your heat transfer here? No heat transfer. So entropy generation is nothing but entropy change here, correct? So that is what you have. You will have that entropy generation is this one, and you will calculate it. And how you calculate S1 and S2? Well, you have your formulas for ideal gas. Which formulas you are going to employ from here? Remember? Remember to distinguish ideal gas. You distinguish ideal gas and solids and liquids. Here are your formulas, right? Here are your formulas that you will employ. So that is what you see for ideal gas. S1 minus S2, you will have it like this. That will be your formulation. If you have nitrogen, if you don't have air but particular gas, you should be able to deal with bar values. Remember the relation between bar values and real values. Bar value, if when you multiply or respectively divide by molar weight. Instead of R, which is specific gas constant, you will have universal gas constant. Please remember. Please remember all this, and we discussed it before the Thanksgiving break, but that's how you solve. Remember what is S0 and how you calculate. Right? Same story here. So for instance, you have your home, that's problem number 6. You have a similar homework problem. And intentionally I give you this rigid tank. There is another problem about tank. It's problem number 8. What stated the problem number 8? Please read. It's stated. Let me enlarge it. It stated you have a rigid tank which contains 10 kilograms of nitrogen given pressure and temperature. Again, you have, so what does it mean? You have state 1, correct? And basically make sure you will be able to convert these temperatures into Kelvin. So it will be 600 Kelvin, correct? Then your nitrogen, unlike previous situation, is gradually cooled. So heat is taken out from your system. It's gradually cooled to 27 degrees Celsius, which will be what? Which will be state 2, which will be 300 Kelvin. So unlike previous situation, here temperature drops twice, right? And there is heat loss to the environment. And the same story, please determine the pressure of nitrogen at state 2. Employ exactly what we just discussed here, right? Employ exactly what we did. What you did for chapter, for problem 6, you can exactly do here. What you did here, it will be exactly the same story. You can find second state. It's exactly the same. But realize now that T1 and T2 will be different, right? What else is asked here? Calculate the change of entropy during this process and find the especially heat losses. So yes, please make sure you can employ balance, first law of thermodynamics, formulas for entropy and balance for entropy. That's what you expected to employ, right? Sorry for dealing with this computer. Yes, so that it is how you'll calculate S2. You use exactly the same formula that us. You use this formula like here, right? That is your formula. But since we deal with nitrogen, we use its counterpart for unit waste formula. So this will be your formula. To get it, you will get this formula, you divide it by mass. So basically that, what you will have, you will get that S2 minus S1, it will be what? You can see it will be nothing, you divide, it will be S naught bar values divided by molar weight. That's how you calculate this value. Now it will be question, again, similar story, how you'll calculate heat transfer. Employ first law of thermodynamics and calculate. Employ first law and see what will be heat transfer. This time you have cooling, but there will be no boundary work. So you will get that Q is equal to just mu minus M1. How to get U? You can get it from the tables, but make sure you know how to switch from bar values to molar weight. It's just chapter 4, just practice from here, just here lectures. That's what you need to know. The key point to understand what formula to use. Another question. Problem 7, where we have potato of given diameter. But you consider spherical potato of given diameter, and the stated that this potato it's uniform and it's uniform at given temperature, and then it's dropped to the water at another temperature. You know density, you know specific heat, and we want to find heat transfer of this potato to the environment, as well as amount of entropy generation. So what you should realize here, what you should do. Key point here to realize is this is not ideal gas. Here we deal with incompressible substances. So here you are. Here you are. So basically, this is the formulas you are going to use. You use incompressible substance. So your change of entropy will be given by this value or even approximated like this. You know T1, you know T2. How you will get specific heat, it's given. I told you it's not CP, it's not CV, it's given value. And how you will find mass? Okay, you know diameter, you will find volume, you will find density. That's something from here you will be able to calculate. So your potato, you should be able to find your mass. You have given density, you have given specific heat. That is your mass. You calculate mass like rho v, you calculate it. And then what you will do is potato, there is no work done in the process. If you want to find heat transfer, what you will have? You will write that is equal to energy change mu2 minus u1. So it's exactly the same like we considered before. For entropy generation, write down balance equation for entropy. And here there is heat transfer. So entropy generation, what will be? It will be entropy change in the system plus entropy transfer through heat. That's what you employ. You will have that entropy generation, it will be what? It will be delta S minus heat over T. Why we have it like this? Because heat goes up. And key point is realize that this is a boundary temperature. This is still your homework and I want you to solve it. So, and please understand me, I show you a piece of the solution. I give you the hint of the solution. I told you many times, what I want you to do. I want you to look at this, after which, I want you to understand it and close all your notes, come home and solve all the problems from scratch. All these problems you have solved from scratch and submit. Definitely you can, our lectures is recorded, you can hear it and you can actually write it down and submit it. You will have good score for your homework number 7B, but it will be negatively impacted on your final exam. Your final exam is really most important, much more important than what we are talking about here, right? So please take it seriously. By tonight, please submit this homework if not yet. Please do it yourself. I know it's not easy. But it's okay if you are not excellent in this homework. It's last homework, it's difficult homework. By tomorrow, I post my solutions, Dr. Mobain's actually solution. So you will see it, you will check it, and make sure that by your exam, you understand how to solve all these problems. And on Thursday from 11 to 1, you will have your final exam. So like what you should do in your final exam, I send you I send you supplementary materials. Remember, I send you tentative list of equations, tentative topical overview. Well, topical overview is not tentative, it's real topical overview and summary slides. I do recommend you to go slow through the summary slides. Now I don't have time for this and no reason because even in one lecture, I cannot cover 70 slides there. Go through. But slides is the last source of your preparation, right? Slides is the last that you have. Key point, you read your textbook, go through lectures. All our lectures are posted. Well, today is the lecture number 38. I'm skeptic if you have time to rehear 38 lectures during a week. Maybe not, but you can rehear some fragments of them. Or if you really know nothing, unfortunately, you still have chance to hear it. 38 hours is just 2 days, just listen. I'm a little bit joking, but make sure you understand everything about your final exam, how it will be. So you know how was exam 1, exam 2, exam 3. Final exam, it will be something like this, but extended. It will be 2 hours. So again, it will be similar structure. It will be multiple choice questions. It will be some simple calculation questions. It will be some other problems, and it will be several like big problems with a task to solve. So altogether, it will be maybe 7 tasks, something like this. It will be about 10 pages of the entire manual, so it's comprehensive. But everything's the idea is still the same. So you don't have actually much time to think about it and to learn. You are expected to know it. And if you solve the problem and you see you spend 20 minutes and you don't have answer, something goes on. 1 point. Second point, it's still engineering class. So please realize that it's not like I ask you to employ formulas and grade how you employ mathematics. You should understand what you're doing. And please don't do silly mistakes, because silly mistakes will mean that you don't understand the topic and your grades will be really deteriorated. What I mean silly mistakes? Something really which means that you don't understand the topic. Say negative temperature in Kelvin, negative pressure, negative entropy generation, quality larger than 1. If you do something like this, it means that you don't know what you're doing. Confusion of open and closed system. Confusion on work done by the system and on the system, right? It will simply mean that you don't know what you're doing. And again, I know you're very careful, you care about your scores, and that's normal. But please realize that typically when we grade students, very seldom the scores is in a board line and you don't see it. Typically we know the scores, and you may approximate and understand your scores. So I tell you the same that other faculty members, maybe like Dr. Musina all the time, talk to all the classes he teaches, that what is A? What is score A? A means that you really very good, you understand everything, you can solve all the problems, there are no gaps. Well, sometimes you can do silly, a little bit, not silly, but some mistakes, some negligent. That's why we start A from 90 points, not 100. What is B? B means that you still can solve potentially any problem. There are no gaps in your knowledge, but on regular basis, you do mistakes. So that's why you deteriorate your grades. That's why you always do some mistakes. Maybe you didn't have time to practice. Maybe you're not strong in the math. You're not strong in this topic, but there are no serious gaps. So you end up with B because you regularly do some mistakes. C means that you already have some lack. There is some type of problem that you are not ready to solve. You don't know how to. If I give this problem now, you're not solving. But maybe everything else you understand. And D, F, and so on, it means that you really get stuck. You really stuck at some point and cannot continue. So and I don't see your eyes now, I don't see you. You know yourself in these categories that I mentioned, where you are. You can tell yourself where you are in this category, and you will know your score. Do you understand everything or not? Don't tell to me, tell to yourself. If you do mistakes, does it mean that it's like occasional mistakes or not? or you will do this mistake again in the final. So if I tell you statistically, if you did well in all exams, you should be okay, most likely. But again, every year we have somebody who fails, somebody who get like 50 out of 100 in exam, like this. So please realize, again, we try to be generous. So again, like if you have 89.5 or 89.4, I give you a minus. So don't worry about these small things. You'll be okay. So don't just fight for some 1 point. But again, we cannot change much. People ask about curving. We don't, I tell you why we don't curve. Because you saw bonuses, bonus quizzes, and bonus tickets. And I already see that a good portion of you will have more than 100 points. Some of you may end up with 108. So if we curve, it means that everybody who has 108 will get 100, and everybody who has 90 will drop to 84. I don't think you want it. So how you will prepare for your exam? So again, key point of this course, it's everything is continuous, and you go one by one. That's why in chapter 3 we had exam. So still chapter 3 is backbone of this course, correct? And if you stuck at chapter 3, if you still stuck at this point, I don't think you need to know entropy. You will not survive with it. You should do chapter 3, then chapter 4, chapter 5, and one by one, and continue. And that's why I told you, if at your final exam you don't know how to use property tables, you have no chance to pass. You will not solve any single problem in your final at all. Even if you understand entropy, you will not be able to use tables to calculate it. In contrast, I told you example who people who get C if you have some gap, small gap. If you don't understand entropy, but you are really good in everything else, probably you will somehow pass this course. But definitely not with A, and maybe not with B, but you will solve many problems in your final. You will solve part of the problems. You see how our problems look like. You start with chapter 4 and 5, and then continue to entropy. So what you should do to be prepared? Please check your exams. All of you did exams, and your marked exams are available. So check them. Please understand what mistakes you do. Please make sure that now you will not do this problem. If you're really not sure if you know the topic or not, take your exam and do it again. Just sit now and spend 50 minutes to do exam 1, spend 50 minutes to do exam 2, spend 50 minutes to do exam 3. You have time for this. If you really need it, if that exam was bad. And you will see how it is. If you cannot solve it now again, so you're in trouble. All homeworks. You have all the homeworks and you will have all the solutions. I know it's too, well, maybe you, well, the best idea that I would ask you, I would suggest if you have time, again, solve all the problems of all homeworks. Maybe you will not have time for it, but you have the solution. Make sure you go through all solutions, especially all answers of multiple choice questions, and make sure you understand it. And tell me, and again, understanding, there are two ways of understanding. One way of understanding is when I solve the problem on a blackboard and I show you a slide with a solution, and I talk, you listen to me and you understand what I'm talking. It's good. It would be bad, it would be much worse if you don't understand me. But it's still not guaranteed that you are solving something. You should be able to solve problem yourself. So when you read the solution, answer to yourself, would you solve this problem now? And now say, okay, imagine that answer is known, but question is not known. If the question was find isentropic efficiency, ask yourself, if isentropic efficiency is known, but H2A is not known, will you find it? If yes, great. If not, it's time for you to close this node and solve this problem right away. That's what you should do, because you are at risk to not being able to solve it at your final exam. That's what you should do. Go through all the slides, of course, but key point quizzes, and I post solution to all quizzes, right? Not exams, but quizzes, because you had the same quiz for all the variants. All quiz solutions are posted, and quizzes are really was good hint about what exams consist of. So again, and you can do it promptly. Do all quizzes, exams, homeworks. Go through the solutions. If you really know how to solve these problems, great. If not, you still have 6 days to get prepared. You still have some time, and please do. And do it one by one. First exam 1, then exam 2. If you don't know property tables, don't go to entropy, right? Okay, I really wish you the best. So please again evaluate this course. Please submit homeworks to me, and I hope I really wish you the best. But if you have questions, please. No, there are no solutions to exam anywhere. I will tell you why. Several reasons. First of all, you have different variants. So it's impossible that you will learn you will know all variants, and you will start confusing your variant with somebody's, and it will be messed up. We had this bad practice before. And again, you don't know which variant you may have at the exam. Second point, very simple. And two reasons. From year to year, we cannot change all the problems. And now we also realize that why we invent our problems. We don't give you problems from textbook. We don't give you homeworks for an exam from textbook, from manuals, because we know some solutions exist online, people can buy it. So we don't give solutions to exam just because we don't want you to be addicted to it. Because if there are solutions to exam somewhere, I will tell you what would happen. You will practice, either you will start writing some notes to hide it for exam, which is illegal, or you will just start practicing the exam, and you will do nothing else because you assume it's the best. So that's why you have solution of the homeworks because it's good template for everything. But exams, it's your task to understand what you did wrong at your exam. In fact, I am available if you need me to, and the TA Eric, I hope he will be busy with his exams, but if he has some claims, I think he will be available to address. Okay, more question. Are bonus points we got throughout the semester going to be added to a final grade? Well, bonus, okay, good, very good point. If we got 2 points. Yeah, a very good point. So your all the bonuses you got goes to your cumulative score, not final exam, but your cumulative score, which is even better for you. So let me explain like this. Your homework, each homework costs 1.25 points, a small one. So all your homeworks are 10 points, okay, 10 points. Exam 1, exam 2, exam 3, its maximum give you 20 points, right, for your final exam. And the final exam is 30 points. Altogether, it's 100. So from here, you get your cumulative number. Let's say you have like 85. Then to this, we are adding what your bonuses are. So if you have 85 and you have 2 bonuses, it will be 87. And in addition, if you wrote good quizzes, if you get 3 more points from quizzes, it will be 91. Well, how can we tell you how many points you have? Your point, well, on eCampus, everything is posted. Go to the column, there is column called bonus. And here you see bonuses you got through your activity in the class and during the lecture time. I typically give 0.5 point for each activity. And also there is like quiz 1, quiz 2, quiz 3, quiz 4. You will see how many you have. Quizzes gave you minor points, but gave something. And please understand, all together you may get more than 10 extra points. And I don't know this year you did not pass, but I tell you, I had years when there were excellent students who are from president list typically, so they ended up this class with 112 out of 100. Okay, that it is. That it is. So basically, how you get it. But again, these bonuses are helpful if you did well, and sometimes you misled something, you did not solve something. If you have F for your tests, believe me, bonuses will not help you much. It's intentionally because bonuses cannot be overwhelming. But most likely bonuses may help you to jump, not to drop, to jump from B to A, from C to B. Okay, one more question. For question A, explain part C. Okay, I will do it. Question 8. If you still see my screen, right? you still see my screen, I will do it. So, okay. So here is, you have this rigid tank, remember, with nitrogen. Actually, you should learn it, you know this problem. So you have cooling of nitrogen. You ask about question C here, right? Okay. Heat losses, okay? Why you ask C? I think you should ask about question B, but anyway. Let me check. Part C, okay? But okay. Let me just see go it. So this is your question. You go to part C. What you should do? Very, very simple. Write down. This is you have this rigid tank. Write down first law of thermodynamics. Here is the law of thermodynamics. What is bound? What is work done here? There is no work. There is no work, correct? So your heat transfer is nothing like m delta U. It's exactly like you did in chapter 6 that you calculate. How you can find U1 and U2? How you can find U1 and U2? It's air, it's nitrogen, right? It's nitrogen. Go to the table and consider, because you have cooling from one temperature to another. What is your initial temperature? Your initial temperature is 600 Kelvin. Your final temperature is 300 Kelvin. So what will you do? Let me see here. Go to your tables. It will be what table? What is nitrogen table? I think it's here. Okay. What? Okay. And then I should. Okay, table 12. I should have turned. Okay. Yeah. To go to what is nitrogen table here? Nitrogen table here is the following. Nitrogen table is table, I think 19. Oxygen is oxygen. Here is oxygen. Yes, it's table 8. So table 18, you go to table 18. So what are your temperatures? You have initial temperature 600 Kelvin. You're here, you have, let me again increase it for you. You have initial temperature 600 Kelvin. So you are here, you'll get it here. So here you have 600 and you have 300 Kelvin. For 600 Kelvin, here is your U value. If you know H value, S value, they're there. For this is for 600 Kelvin. That is for initial temperature. For 300 Kelvin, you have this value for you, right? Here it is. So you get. But what you must remember, this is what is U. It's U bar. So it's specific per unit mole, right? It's mole. It's kilojoule per kilomole. While U used to be use kilojoule per kilogram. How to switch from kilojoule per kilomole to kilojoule per kilogram? Exactly. Divide by molar weight if you want to have unit mass. So what you will be doing here? Here it is. That's you go to your table. You took it from your table, and then here you will calculate the value you get from the table and divide by molar weight of nitrogen. Molar weight of nitrogen, you can get it from the table, or you may remember it's from periodic system, it will be 28. N is 14, so and N is 14, so N2 will be 28. And I do recommend you remember these basics, that mass of hydrogen is 1, mass of carbon is 12, mass of oxygen is 16, atomic, I mean, and mass of nitrogen is 14. For molecule, you have N2, it will be 28, oxygen will be 32. It's easy to remember. That it is. Does it make sense? Okay.
Yeah, that makes sense. I was just getting like messed up with the work for some weird reason, but yeah, once you said that, like that there was no work at the beginning, I knew what else to do from there.
Well, that's okay. That's all. I understand. Let's see. This homework is really comprehensive. We intentionally give you quite difficult homework 7B because that is the only way for you to get prepared to the final exam. And we have two goals here. One goal to recall chapter 4 and 5, and that's what we are doing here, and that's what you're doing in problem 6. We request you to recall it because you may forget, right? And second, isentropic efficiency. That's why you have problem 3, 4, and 5. I do request you do this homework very seriously in detail. It's last but not least. And in your final exam, it will be isentropic efficiency, I suspect. So this is something that you still need to know.
Thank you.
Okay, more questions, please. Okay, if not, I wish you the best and have a good finals, not only my final, all finals. Have a good break. Key point that I do hope that by January 18th, when next semester starts, you all don't get coronavirus or get vaccination by the time, and we all stay healthy. That's most important. And I wish you have everything good, but we still meet next Thursday, and please be in Zoom, right? Okay, thank you. Then I will stop sharing my screen and I still post this lecture anyway. No more questions?